Okay, this video is going to act as a review for the final exam for Calc with Trig. I'm going to break the video into a couple of parts. This first part is going to focus on integration, and it's going to follow along with the first page of our review study guide, labeled integration. You can see the format of the test is 25 multiple choice questions. You will be able to use a calculator on it. We'll only really help you have a calculator on a couple of problems, but by all means, you're welcome to have a calculator. And it will take 60 minutes. So it should be, a couple of minutes per question should get you through it. Some will take longer, some will definitely take a lot less. However, with integration, which is this first part, what we've done most recently, what you've got here are, several bullet points, A, B, C, D, E, and F. I've got examples that are comparable to those that are going to be on the test that I'm going to work through. And it's really just your job to make sure that you can follow along with these examples, make sure that you could do comparable ones on your own, and then go back to any note sheets and homeworks and practice that we did throughout the year from that point on, if you need any extra practice on that stuff. So it's all there for you. Okay, so for the first bullet on integration, letter A, evaluate indefinite integrals. The note sheet or the study guide mentioned that you're going to have one that's going to be a polynomial and then one will be a radical expression. So these are very comparable to what you might see. Indefinite integrals, again, what you're doing is finding a function that has this expression as its derivative. So we just go about, since this is just a sum and a difference of different individual little power functions, we just use the power rule in reverse that we use for derivatives, and we just increase the power of x to the third to x to the fourth and divide by 4. 2x squared becomes 2x cubed over 3. Negative 5x becomes negative 5x squared over 2, and then 1 becomes simply 1x, or just x, and then of course we have to remember our constant of integration. So really simple, straightforward process there. Just got to keep your mind clear as far as that you're doing integration, not differentiation. For the second one, we've got a radical expression which would require us to rewrite the cube root of x as x to the 1/3 power dx. And then again, we just do the power rule. We're going to increase the power by 1. So x to the 1/3 increasing by 1 would be 3 more thirds, which would give you x to the 4/3. And then dividing by 4/3, of course, is the same as multiplying by 3/4. And then just add the constant of integration. So just a couple of really straightforward indefinite integrals will get you through whatever you need for the final. Those are very comparable to the ones that are on there. So nothing too major there. To evaluate a definite integral, again, same idea. We're going to use the power rule. Very straightforward integration here. No special techniques required to do this. Just increase the power by 1 and divide by the new power. And of course, with the definite integral, what we're going to do is wind up with a particular value. It's going to be a numeric value that's going to tell us how much area we would have bounded by this curve and the x-axis between -2 and 2. So negative x to the third is going to become negative x to the fourth over 4 plus x becomes x squared over 2. And we're going to evaluate that between -2 and 2. And what that means, of course, is we're going to plug 2 in to each value of x and then subtract what we get when we plug -2 in. Now this is a little tricky here because we've got some negative signs. We're going to be raising -2 to powers and things. So we want to be careful with that. This problem is rigged, however. You may have recognized this is an odd function. So this answer is going to turn out to be something we should definitely be able to predict that I'll talk about at the end. But anyway, here we go. Negative, the opposite of 2 to the fourth over 4 plus 2 squared over 2. And then we subtract what we get when we get the opposite of 2 to the fourth over, -2 to the fourth over 4 plus -2 squared over 2. So again, the 2 got substituted here and here, and then we subtract what we get when we plug -2 in for those spots. And now evaluating, this is the opposite of 2 to the fourth, which is -16. -16 over 4 is -4. 2 squared over 2 is 4 over 2, which is 2. Then we subtract what we get inside here. This will, of course, be 16. And then will be the opposite of 16 over 4, which is -4. And again, this is going to become 4 over 2, which is 2. And you might recognize that we have -4 plus 2 minus -4 plus 2, which is going to give us a net result of 0. After we distribute this negative, and we get a plus here and a minus there, we get a net result of 0. And that was to be expected. I don't know if anybody noticed that, but we had negative x cubed plus x, which is a cubic function that would be symmetric about the origin and look something like that. So the areas that we were getting, whatever positive area we might get from -2 to 2, would get canceled out with the negative area, because remember, area underneath a curve is represented as negative, so that red area would cancel out that blue area, and this red area over here would cancel out that area there. So the answer of 0 was to be expected there. Okay, another way you can be asked about a definite integral or evaluating a definite integral is when you're given a graph of a function, as we are here in this example. Granted, it's a graph that's made up of some straight line segments, so it's a graph of f of x, and we're being asked to get the definite integral of f of x from -2 to 5, which means let's find out how much area we have bounded between the x-axis and this blue curve as we move from -2 to 5. So this basically just becomes a little basic geometry class question where we have to add up the area of these little regions that are bounded by the curve in the x-axis. So by that I mean, we're talking about moving from here -2. So if we get this area right here, that is a triangle that has a base of 2 and a height of 2, and the area of a triangle is 1/2 the base times the height. So in this case, that's 1/2 of 2 times 2, which is 1/2 of 4, which is 2. So I'm going to put a 2 in there. I have this little black line in here from some notes I did in class. This next portion, this area as we move, in here, that's a rectangle that's 1 wide and 2 tall, so that has an area of 2. And then we have another little triangle here as we're coming down, and that is 2 wide and 2 tall, so 1/2 of 2 times 2 again is 2. So far we have 6 units of area that we've accumulated as we've moved from -2 all the way over to 3. However, this is the tricky part. As we take this last chunk of this last triangle down here, which is also 2 wide and 2 tall, but it is below the x-axis. So that area there, which has a net area of 2, is going to count as negative area because it's below the x-axis. So what we're looking for is the net signed area, and so we would add 2 plus 2 plus 2 and then subtract 2 for a final answer of 4 square units, and that's our answer. So that's a very typical calculus question where you just have to apply the concept of a definite integral to a little geometry problem. The next type of definite integral problem is one that involves the formula for the average value of a function. There's a really straightforward formula that we have to determine that, and for this particular function it's 3x squared minus x. The formula for the average value is on an interval from a to b is how it's the formula is written as we move, in this case, from -1 to 3. As we go from -1 to 3, what we're doing is getting the average value of that function. So the formula is 1 over b minus a, which in this case is 1 over 3 minus -1, times the integral of -1 to 3 of our function, which is just 3x squared minus x. So 1 over 3 minus -1 is 1/4, and we're going to integrate from -1 to 3, 3x squared minus x dx, and we'll get that number here. So we need to use the power rule, so 3x squared will integrate to 3x cubed over 3, and the 3's are going to cancel out, so we're just going to get x cubed minus x squared over 2, and we're going to evaluate that between -1 and 3. So what we have to do now is plug in the 3 and get a value, and then subtract what we get when we plug in -1. So we're going to take 1/4 and plug in 3 and get 27. 23 cubed is 27. Minus 3 squared over 2, which is minus 9/2. Then subtract what we get when we plug in -1. -1 cubed is -1. And then when we have -1 squared, that's going to be 1 over 2, but we are subtracting 1 over 2. So we can clean up what's inside there. And it looks like we're going to get 27 plus 1, which is 28. We get 1/4, of course. And inside we've got 28. Basically, this negative is going to cancel out both of those. So we get 27 plus 1 is 28, and negative 9/2 plus 1/2 is negative 8/2, which is negative 4. So 28 minus 4 is 24. 24 divided by 4 is 6. So that is the average value of the function. So definitely a little work to do there, some arithmetic. But again, having a calculator on this exam, for this average value problem and for the other definite integral that I did on the previous slide, you can always use your calculator using the math key and then choosing option 9. And that gives you the definite integral with the template for what you need to integrate. And that's literally just punching the numbers in. So that could really help in a problem like this where there was a lot of arithmetic. You could just simply compute this integral on your calculator and then remember to take 1/4 of the answer. Because again, the average value is basically taking the total area and dividing it by how wide your interval is. And again, all these questions, that one in particular, are very close to what you would see on the actual final exam. Next, for the integration portion of our exam, applying the fundamental theorem of calculus, which has to do with kind of the idea of what we just did with the definite integral, providing some area, but also kind of in the general sense of the relationship between integration and differentiation being sort of inverses of each other. So now you get a question like this where you are given the definition of a function g of x, which is expressed as an integral of f of t from -2 to x, as we see here. So we're going to integrate this function f as we move from -2, where it starts, all the way out to whatever x is. And we could be asked, you will be asked, probably one or two particular values. You'd be given a function like this, you'd be given the graph, and then you'd be asked for a couple of values. So I'll just kind of take you through the first couple that we have here to make sure you know what we're doing. And so as we move from -2 to this first one says, g of -2. Well, remember, g of x, whatever x is, goes right there. So we're literally, for this first problem, going from -2 to -2, which means, of course, we're going nowhere. So it's asking us how much area are you collecting as you move from -2 and then don't go anywhere. So, of course, that answer is 0. But the next one is g of 4. So that means we're going to be integrating as we move all the way out from -2 to 4. So we're basically getting all this area for this triangle underneath there. That triangle has a base length of 6 and a height of 2. And again, 1/2 of the base, which is 6, times the height of 2, is going to be 6 square units. So g of 4 would be 6, and that represents the area that we got bounded as we move from -2 to 4. G of 8, interesting, because now we have some area that's below the x-axis. This one is 4 wide, it goes from 4 to 8, and it's also 2 tall, so 1/2 of 4 times 2 is simply 4, but again, these being below the x-axis, the area is considered as -4 square units. So we had accumulated 6 square units as we got through this stuff, but then we lost 4 units here, which gives us a net, by the time we get out to 8, a net area of 2 square units. So you can see, again, if we were to continue on this, if we went all the way out to 10, we would get another little triangle's worth of area. It looks like it has an area of 2 that's above the x-axis, so it would be positive. So if we were asked about g of 10, we would just add 2 to the previous area we just got, which was 2, and we would come up with a net area of 4 by that time. Now, questions about a situation like this in general. Not saying that you're going to have 4 questions like this, but you might have any one of these questions. So because g is the integral of f, what we learned this year is that means that the derivative of g is f. So if g is the antiderivative of f, the derivative of g is f. That's our relationship. These things kind of mean the same thing. So when we're looking for a local max, we need a place where the derivative of g goes from positive to negative, and that's going to give us a max sitting at the top of a hill. So the derivative of g is f. So essentially all we need to know is where does this blue function go from a positive value to a negative value? Well, f starts at 0, goes up to 2, and then it comes back down to 0 right here. So it has positive y values here, then it hits 0 at 4, then it has negative y values here. So right at x equals 4 is where f, which again is the derivative of g, so the derivative of g goes from positive here to negative there. So that's the place right at x equals 4 where we'd have a local max. And again, that's because g prime goes from positive to negative. Now, a local min, that's where we're going to go from a negative derivative to a positive one, and that's going to happen here at 8, because the derivative of g, which is these y values of f, goes from negative here to positive there. So we can say at 8, when is a function increasing? Well, again, my little picture from before, this function's increasing right here because it has a positive slope. So what we need is for the slope of g, which is f, to have positive values. So g would be increasing when f has positive values. Well, the positive values for f are all this stuff up here when it's above the x-axis. Those are positive values of f. So that happens between -2 all the way up to 4, and then they're positive again from 8 to 10. So again, we're talking about places where f is above the x-axis, from -2 here to 4 here, that's above the x-axis, and then again from 8 to 10. And g is decreasing, as you might imagine, is going to be when f is below the x-axis, which looks like it happens from 4 to 8. And there we go, from 4 to 8. So, we covered, 3 problems here and 4 more over here. There's not going to be 7 questions on this on your final exam. However, you could get a collection of maybe 2 or 3 of those questions that could pop up from one single graph. Okay, now just for the last 2 bullet points on integration for this final exam review. One is a really straightforward concept. It's the second part of the fundamental theorem of calculus, where we really formalize that relationship between integration and differentiation sort of being inverse of one another. So if a function is defined as an integral from a constant up to a variable, and so in other words a function of x is defined from some constant, doesn't matter what it is, 6, 2, -3, 13, 57, whatever, from some constant up to x of this integral, this integrand here, the square root of the quantity 3t squared minus 1, but then you're asked to take the derivative of that function. There's 2 ways we could do this. We could try to integrate this thing as a definite integral and then plug in x and subtract what we get when we plug in 6. And I think you could see that that would turn out to be, something with a bunch of x's in it, blah, 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 x's, maybe with square roots and all this stuff. And then we would subtract what we get when we plug in 6 and maybe get some number like, 13 or something like that. Well, that's great. But when you take the derivative of this function, which is what we're being asked to do, well, you're going to reverse that integration process, and you're going to get right back to whatever this integrand was. So in other words, to integrate something and then take the derivative, you get right back to where you start. Meanwhile, when you take the derivative of the constant, it's just going to go away. The derivative of the constant is 0. So all we need to do to answer these fundamental theorem of calculus part 2 questions is literally just replace the t with an x, and our answer would be the square root of 3x squared minus 1. So that question, you're going to see something very similar to that on the test. Should take you about 3 or 4 seconds to answer it. All you have to do is imagine this x taking the place of that t, wherever that t shows up in the function, and you're good to go. That is your solution. Don't do anything. Don't try to integrate it. Don't try to take the derivative of it. Just literally take the integrand out and replace any t's with x's, and you'll be all done. Now, lastly, this u substitution problem. I'm not going to have you have to create a whole u substitution problem on your own, because with a calculator that's kind of silly. You could just literally plug the integral into your calculator. It would give you the answer. What I am going to do, though, is give you an integral that would be fairly complicated to compute and suggest a u substitution for you. So, for example, in this particular problem, we've been given this integral here, the integral from 0 to 2, 1 plus the quantity 2x squared over x, and it says it's equivalent to, and what we're going to do is, we're going to come up with this integral after we make the u substitution and du and take care of everything. So in a multiple choice format, only one of the answers will be, what we're supposed to get when we do that. So let's see what this thing would look like if we were to do this u substitution. So the first thing we do, if we know that u equals 2x, is we go get du, which of course would just be 2 dx. Now we look at our integrand here, and we don't have 2 dx, we only have dx. So the first thing we're going to do is take 1/2 of du and say that that's equal to dx. So now we can start to recreate our integral. We've got 1 plus 2x, which of course is u. So we have 1 plus u being squared. And then it's over x. Well, we don't have an expression for x here anywhere in our work. We know what u is. It's 2x, and we know that 2 dx, or that dx, equals 1/2 of du. But we don't have an expression for plain x. But we can get one from this relationship. X, of course, would be equal to 1/2 of u. So I'm going to put 1/2 of u down here. So now we've got the 1 accounted for, we've got the 2x accounted for, and we've got the x accounted for. Dx is simple enough. Dx is right here. It's 1/2 of du. So I'm going to put the du here and the 1/2 out front. And we're almost there. A couple of things I don't like. One is that we don't have our limits accounted for. This one is 0 and this one is 2. So we're going to go off to the side and say when x equals 0, and we look at our formula right here. If x were to be 0, 2 times 0 is simply 0. So our new limit is 0. But when x is 2, what's u going to be? Well, put a 2 in here for this x, and we would get 2 times 2, which is 4. So our new limits are 0 to 4. So now I like this, except it's a complex fraction. We are dividing by 1/2 of u down here in the denominator. So I would like to get rid of this fraction that's down there and realize that if you're dividing by 1/2, that's the same as multiplying by 2 over 1. So now that cleans up our integrand a lot, and actually it really does a nice trick, because this 2 would then cancel this 2, and we'd have simply the integral from 0 to 4 of 1 plus u squared over u du. So, of course, if I were offering this as a multiple choice question, this would be one of the choices, and this, of course, would be the correct answer. I'd tell you one thing I'd probably do is have the very same answer, but I'd have the original limits of 0 to 2 there, which would be the sucker answer, where somebody forgot to change the limits over. So there's lots of ways we can make little arithmetic mistakes there. But essentially that's what you're going to have to do a u sub. You're just going to have to kind of recreate the integral, but you won't actually have to find out what this integral is. All right, so that wraps up the integration portion of our review. And so there's a next video that's going to take you through the bullet points for differentiation. And that one I think I have as 3 separate videos. One's going to be the first several bullet points, and the last 2 bullet points are taken up on separate videos.